Okay, we can start. So last time we introduced the idea of predictive coding, and we have introduced the simplest way of predictive coding based on linear predictor. And we said that this linear predictor is closely related to the least square approximation, to the method of least square estimation that was developed by Gauss and Legendre. And the final structure that is used for prediction is this simple FIR filter, where this abbreviation FIR comes from finite impulse response digital filter. And to explain how it functions, this element z to the -1 is nothing else but one step delay. The signal at its input is delayed by one sample, such that at the output we have input from the previous time step, and so on. In this way we get exactly what we need in the context of prediction source. We construct it in this way these red samples that are used as a prediction source. To predict this green sample, we use, in this example, 10 preceding samples, 10 red samples, and these 10 red samples are exactly at the outputs of these delay elements. So this is a sample from the previous step, from 2 steps in the past, 3 steps, and up to p steps in the past. And they are multiplied with corresponding predictor coefficients, alpha 1, alpha 2, and up to alpha p. And this coefficient set, as we said, it is found in the process of estimating the optimal predictor, and it is fixed. So once found, it is applied for quite a long signal, I would say, as long as possible. To be effective, if the spectral characteristics of the signal are not changing with time, then really we can use the same predictor coefficients for the whole signal. But what happens with the real signals, like speech or audio, is that their correlation properties change with time. They are not stationary. And that means that in real world applications, we cannot use fixed coefficients for, let's say, 1 minute of speech or for 1 minute of audio. Otherwise, such predictor would not be efficient in predicting the next sample that comes. So it is better to do it on relatively short segments of signal, like speech or audio. And these short segments are typically not longer than 10 up to 20 milliseconds. So 10 to 20 milliseconds segments are extracted from the signal, and we will see later on, for such segments, we compute the optimal predictor coefficients. And once we have them, we simply use them to predict the next sample. But nevertheless, if we want to do the reconstruction, the decoder also must have these coefficients to be able to reconstruct the original signal from this prediction residual. So we have not said yet anything about that, but the basic idea is I would like to use this prediction residual E of n and use the inverse of this system A of z to reconstruct the original signal X of n. So that's the basic concept of predictive coding. So instead of directly quantizing X of n, I will do the prediction, subtract the prediction from the signal, get the prediction error or prediction residual, and this prediction residual would be quantized, sent to the decoder, and the final step that must be done on the decoder side is to have the inverse of such system to reconstruct the original X of n as close as possible from quantized prediction residual. So it is the basic concept of predictive coding. Okay, the transfer function of the predictor can be also written in Z domain. So this Z domain is something that is equivalent as Laplace domain for continuous time systems. When we have continuous time systems, when we want to solve differential equations, instead of solving differential equations in time domain, what is a bit complicated, we usually go to this Laplace domain, as we call it, or frequency domain, because in this case, the operations are converted to some kind of polynomials. So you have some polynomials that represent the system, polynomials that represent input signal, output signal. You can do very easy the operations that are otherwise convolution in time domain. In spectral domain, they are simple multiplication. Analog for the time discrete domain is this Z transform. With Z transform, instead of operating in time domain with time step n, we go to this frequency domain. And this frequency domain is denoted with free variable Z, exactly as it was S for Laplace domain, as frequency variable. Now it is Z for discrete systems, but the definition of Z transform is very simple. Here. So to have this Z domain representation of a signal, I will simply take signal samples, multiply them with Z to the power of minus n, and accumulate from either 0 to infinity if the signal is causal. So if it is 0 left from the origin, from n equal to 0, if the signal is 0, then I only have to add from 0 to infinity. It is similar to the original continuous time domain representation using Laplace transform, where we had x of t e to the power of minus st dt from t either 0 to infinity or minus infinity to plus infinity if the signal also has this anti-causal part. If the signal is no 0 left from the origin of the time domain. So this here is Laplace domain, Laplace transform, and this is Z transform. Z transform. Okay, we will not go any further in this because the students do not have any courses like signals and systems. They have problem understanding this, so we will only cover this from phenomenological aspect. Okay. So the idea is that once I have such a system, then transfer function of a system can be represented as a simple polynomial. How do I solve it? So let's say that I have in time domain x of n, and that goes into a system P of z, okay? And we have the output x tilde of n. If I convert this signal to Z domain, as well as this one, I would have x of z, and I would have x tilde of z here. And these two are connected through transfer function of the predictor. And this transfer function is a simple polynomial. So this P of z here is some alpha k, z to the power of minus k, k from 1 to p, okay? And I can get this x tilde of z by simply multiplying x of z with this P of z. Okay? Okay. Now, if I take this larger system, this A of z, so this A of z, its output is not x tilde, but its output is A of n, E of n. Okay, the larger system. Then, completely analogous to this E of z is then equal to x of z times A of z. We can write it with red. A of z as red. Okay. So the operation of a filter on a signal in frequency domain can be represented as a simple multiplication. In time domain, corresponding operation is convolution. So what is convolution in linear domain, linear convolution? We have the simple multiplication in the frequency domain, and that is the main reason why we use Laplace transform for continuous systems, why we use Z transform for discrete systems. For such systems, for linear systems, we have this identity that convolution in time domain is then a simple multiplication in frequency domain. Now that we have this E of z, so the transfer function of this red system that has the E of n at the output, then to reconstruct the original, let's say x of z, so if I have this E of n, without any quantization, if I have E of n at the input, I ask myself, what do I have to put here to have x of n at the output? In z domain, it is trivial. So we have E of z here, we have x of z here, and as we see, they are related as it is written here. So if I want to compute x of z, I have to divide this E of z with A of z. Of course, it is some kind of polynomial. So this here is this polynomial. So what I have to do to find this x of z, I have to pass prediction residual through the inverse system that has this A of z in the denominator times E of z. And this reciprocal system, this inverse system, will be denoted with h of z. So this is the transfer function of the reconstruction system that reconstructs original signal from prediction residual. Since this A of z can be also represented as 1 minus P of z, because this subtraction is simply z transform of x of n is x of z, nothing else. And this here, x tilde, is p of z times x of z. So this subtraction gives us simply 1 minus p of z. So this is the transfer function of this larger system A of z. So in the end, I can write that this h of z is simply 1 over 1 minus p of z times E of z. So this system here is called reconstruction filter or inverse filter. Okay. It is inverse of the prediction filter. Okay. So the question mark in this block is, okay, this is h of z. So h of z is this unknown system that is used to reconstruct the original signal. But of course, so far we don't have any quantization. We started from x, we computed prediction residual, and directly without any quantization reconstructed the original signal x of n by passing it through the inverse system, h of z. So these two systems, a of z and h of z, they give us 1. They are reciprocal one to each other. Okay? But now the question is, what happens if I have this a of z at the input? So this here is the input signal x of n. I get prediction residual e of n. But now I put here a quantizer. And I get this e hat of n. And then again I have the reconstruction filter h of z. And the output I get x hat of n. For some approximation of the original input signal. So I have some error here. Quantization error. So due to the quantization error, I have the difference between the ideal and quantized prediction residual, and therefore I would also have some kind of error, but not the same error, between original signal and reconstructed signal. So I have reconstruction error. Reconstruction error. Okay. So it is said here. So under certain condition, it is possible to invert the prediction procedure by reconstructing the original signal from prediction error signal. This is done by digital filtering of E of n with recursive filter h of z that has infinite impulse response h of n and a transfer function of this form. So 1 over 1 minus p of z, or if I substitute the actual polynomial for this p of z, it has this form. So that is the reason that we call this a of z is inverse filter and this h of z reconstruction filter. Okay. So, is this really possible to do this inversion? Is it really possible to do this reconstruction? So, what are the conditions that must be met such that this reconstruction is possible? So, again, without going into details, that to understand them, you really need to understand the basics of signals and systems. Let's say that this a of z has roots, certain roots, and that means frequency where this a of z is exactly 0. So this a of z is actually transfer function, and for some z, for some complex values of z, a of z is equal to 0. And these characteristic frequencies are called zeros of transfer function. So a of zi equal to 0, zi blah blah blah. So zeros of transfer function. So for some frequencies of input signal, the output is 0. And once something becomes 0 here, then the question is, how can we reconstruct something from 0? So obviously, you would have to multiply it with infinity to have infinitive gain in order to take this 0 to some finite value, to reconstruct this 0 to some finite value. So this is obviously not possible. Once the signal is cancelled here, if we select input frequency such that a of z is equal to 0, then there's nothing we can do with reconstruction, because otherwise the gain of the reconstruction filter h of z would have to be infinite for this frequency. Okay, and that results in unstable behavior. Such reconstruction filter becomes unstable. And that is the reason that we cannot do reconstruction for those frequencies where this A of z is 0. And as this z is a complex number, so I can plot this ze in the complex plane. And usually they would be either real, so the imaginary part is 0 and the root is on the x-axis, for example, something like this, or they occur in conjugate complex pairs. So this is simply visualization of roots, of these complex roots of the polynomial. So with the polynomial, if this original polynomial, A of z, is 10th order polynomial, it has 10 roots. Just again to be illustrative, so for example, if this P is selected to be second order prediction, P equal to 2, then I have the predictor of the form P of z is 1 minus alpha 1, z minus 1, minus alpha 2, z minus 2. That is the denominator. So this is this A of z. Sorry, this is A of z. Sorry. This is A of z, and this here is P of z. So this is 1. 1 minus P of z, because P of z is this alpha 1, z minus 1, alpha 2, z minus 2. So now I solve this polynomial A of z equal to 0. I'm trying to find the roots of this polynomial, A of z equal to 0. I can multiply this left side and right side with z squared, and I would get the polynomial z squared minus alpha 1 z plus alpha 2 equal to 0. And then you will solve the quadratic equation and get the complex roots of this second order polynomial. And if this P is of higher order, then you would have 3 roots, 4 roots, blah, blah, blah. So for order P, I have P roots. And these roots are, in general, complex numbers, element C. Element C. And I have plotted here examples of such roots. So when the roots are real, they are on the x-axis. But if they are imaginary, complex, they have this y part. So this is the j-axis, this is the real axis, okay, real part, imaginary part, okay? And the problem of inversion or reconstruction happens only if these roots are outside unit circle. So if the magnitude of these roots is greater than 1. So reconstruction is possible for all z absolute value less than 1. So all the roots of this original polynomial A of z, so this zi are roots of A of z. Why? Because once I construct the inverse filter, this h of z is 1 over A of z. So the roots of this A of z in the denominator, they become poles of this h of z. And poles are frequency where this transfer function becomes infinite. It becomes of infinite magnitude. And that is the a reason for instability. So these Zi are therefore poles of H of Z. And it is exactly for that reason that their magnitude must be less than unity. Otherwise, if the magnitude of the pole is outside unit circle, greater than 1, then I will have unstable reconstruction filter. Okay, so we will not go any further, just to understand these basic concepts of stability. So what are the conditions for this stability? What are the requirements? The requirements are such that this A of Z, when I find this polynomial should not have any roots with magnitude greater than unity. If they are all less than 1, then I can construct the reciprocal filter H of Z, and therefore all the poles of this reciprocal filter are stable. Okay, we have stable poles. Stable. So for all roots, their magnitude should not exceed 1. Okay. Enough of that. And now let's introduce one way how we can compute these coefficients using the so-called autocorrelation method. And this autocorrelation method, as we will explain, it guarantees the stability of the reconstruction. So if I apply this autocorrelation method, always the solution A of Z will have roots that are less than unity. So it says here, filter will be stable, reconstruction is possible only if all roots are within the unit circle in Z-plane, which requires that filter A of Z has all of its zeros with magnitude less than unity. And that will be satisfied exactly with the autocorrelation method. And now I will explain the basic idea of this autocorrelation method. It uses slightly modified form of this matrix equation. But I will write the original version of these elements of matrix phi on the whiteboard such that you can compare them with the autocorrelation version. So for the original phi definition, we get this phi of, is it jk or which were the indices? Ik. Phi of I comma k is the sum S or X, okay, we have used X, Xn minus I, Xn minus k. Added over all indices of signal n. And now for autocorrelation method, we use R of what is the index? R of J. R of J. And this R of J is nothing else but something like that. Phi of E plus J comma I plus J comma I. So the idea is the J is actually the difference between the absolute difference of I and K. J is the absolute difference of I minus K. Okay? And as you see from the definition, they have this N, x of m, okay, m, x of m times x of m plus j. So this is the definition of the autocorrelation coefficient. How can I visualize this? This here shows two signals, n minus 1 minus j. Let's say that I have the original finite signal. This x of m is signal of finite length. Let's say that I have only 4 samples of signal. And the other signal is simply shifted by chosen number of samples. Let's say it is shifted by 2 samples. So I am computing R of 2. What I do is shift it in time. Okay. So this is, if it is plus, then this would be x of m plus j, and this would be x of m. So for example, on index, if this is m, so this is sample x of m, and at the same time instant, I have here m plus 2, and m plus 2 is exactly this sample. Okay. And what do I have in the product? Since all other samples are 0, so all other samples are zero because signal is of finite duration. As a product, I only have this pair here. So x of m that multiplies x of m plus 2. X of m plus 2. And I have another sample, x of m plus 1, that multiplies x of m plus 3. And these two factors are exactly shown here. Let's say that I have n that is equal to 4, as in our case, we have 4 samples. And if I compute this R of 2, then this summation goes from m to n minus 1 minus 2. Goes 0. Okay? Goes from 0. So with such indexing, this position would correspond to m equal to 0. And this would be m equal to 1. So this means is x of 0 times x of 2 plus x of 1 times x of 3. And that is R of 2. R of 0 is then simply sum of x squared of m for m from 0 to 3 in our case. So if I take this j to be 0, then I have simply x of m times x of m, because j is 0, from 0 to 3, from 0 to 3. So it simply adds up the quadratic value of all the samples. Okay? If I take j minus 2, I would have exactly the same solution as I have shown here. So for j equal to minus 2, I would get R of minus 2, which is equal to R of 2. You can easily check by substituting such case, then we have this symmetricity. So the autocorrelation function is symmetric in the leg J. This is called leg, delay leg, or autocorrelation leg. So if this J has a negative value, it doesn't matter, we have the same autocorrelation as for the positive delay, positive leg. Okay. And now, if I have the original phi of what they used, ik, yes, phi of ik, it is replaced with R of absolute I minus k. This is for general linear predictor, while this here is for the autocorrelation method. So for the autocorrelation method, we will use this equation R of J, and it is the same as phi of I comma k by simply considering only the absolute difference between index I and k. So you know that on the main diagonal, I and k are equal. 1, 1, 2, 2, 3, 3, blah, blah. And the absolute difference on the main diagonal is 0. Here, the column index is by 1 greater than the row index. So I have absolute difference 1. Here is the other way around. Here, the row index is by 1 greater than the column index. Again, we have R of 1. So at the end, what we get matrix that has not only symmetric form, that was also before. That was the case also before for the general linear prediction matrix phi. But now, as we see, all the values along diagonals have the same value. So the main diagonal has value R of 0. The first auxiliary diagonal upper and lower, they have this value R of 1, and so on. So they have a constant value along diagonals that go from upper left to lower right, and such structure, such property, matrices that have such structure, they are called Toeplitz matrix. Toeplitz, for the surname of one mathematician. Toeplitz matrix. Okay. Due to high prediction efficiency, they are for very large number of natural processes, linear prediction procedure has a frequent application in media signal procedure, coding procedure. Source coding procedure that use linear prediction are collectively called linear prediction coding, or LPC. And one of the first applications of linear prediction for media signals was for speech process, for speech coding, for speech processing. It was later extended to other types of media signals as well. And now we will introduce how it is really done. How do we construct a coder based on this linear prediction? I have already outlined the idea, but now we will show the actual system. There are two basic structures how we can construct coding, linear predictive coding. First is the so-called open loop prediction. It is the one that I have already plotted on the whiteboard. And the other structure for predictive coding is so-called closed loop prediction coding. Okay? In the open loop coding, it is exactly the structure I have shown. So this here is this prediction system that I have here the prediction that is subtracted from the original signal, and I get the residual. So altogether, this is the system A of Z. So this here is system A of Z, transfer function A of Z. I have a quantizer here, and I have the reciprocal system 1 over A of Z, which can be easily visualized just as a mirrored copy of A of Z. So I start from the reconstructed signal x hat of n, I pass it to the predictor, and I get like a local copy of prediction on the decoder side. This local copy, since the prediction source was not the same, here the prediction source is x of n. On the decoder side, the prediction source is x hat of n, which is close to the original x of n, but not equal, because I have some error here caused by quantization. So because of that, this prediction here is not the same as prediction here. So if I would have quantization, ideal quantization with no error, in this case, this x of x hat will be equal to x of n, and prediction x tilde on this side will be also equal to this side, x tilde on this side. And whatever I subtract here, I simply add the same signal here, and of course I should get the ideal reconstruction. Okay, so why do we use such prediction at all? Where is the gain of using prediction? The basic gain is that this E of n has much smaller variance than the original x of n. And we have shown that in order to reduce quantization error, one simple way is to reduce the variance of the signal. So if the variance of the signal is smaller, then I can quantize the same signal with less number of bits, because the variability of this signal is reduced. And such concept is used here. So this is the original input signal. It has some high variance, but if the prediction is good, then this E of n is of much smaller variance than x of n. It was shown in this example for the speech signal. So if these are original signal, green line, and prediction, dotted line, then the prediction error or prediction residual is a signal of much smaller variance, much smaller effective value. And obviously, I should be able to quantize this small variance signal much more efficiently than by quantizing the original signal at the input, this green one. So the basic idea, this predictor would simply reduce the variance of the signal by applying prediction. Okay? Another alternative for prediction coding, predictive coding, is to solve the problem of different predictions. So obviously, one additional source of error is that these two are not equal. One source of the error is caused by quantization. This E of n is not equal to E hat of n, and obviously I cannot have x, that is x hat, that is equal to x of n. That's obvious. But another problem of open loop quantization, open loop linear predictive quantization, is that I have the difference between these two. This x hat on the decoder side is only approximately equal to x hat on the encoder side. And the total error between x and x hat is this difference, but also plus this difference. And my goal is to somehow eliminate this second difference, the difference between predictions. And it is done by using the so-called closed loop prediction. And we will only show the block diagram. So what I have here is a local replica of the decoder, but on the encoder side. Okay. Sorry. I have the original signal, but I do not do the prediction from x of n. I do the prediction from x hat of n. How? So let's assume that this is prediction. X tilde of n is a prediction. So this prediction is not computed from x of n as was the case for open loop. So for the open loop, I use x of n to compute prediction, x tilde. But now I will use x hat of n to compute the prediction. Also on the encoder side, not only on the decoder side. So I will have like a local copy of the decoder on the encoder side. Okay, so I have this prediction here. I subtract it from the input signal. I get the prediction residual, which is being quantized. Okay, now after quantization, I simply add back what I have subtracted here. So the same prediction is simply added back to the quantized prediction residual, and I get reconstructed signal. This reconstructed signal is then used to feed the predictor. So now the predictor on the encoder side also uses the same source for prediction as well as does the decoder. So they both share the same prediction source. And shown on the bottom is the far side decoder. And this far side decoder is exactly equal to this local replica of the decoder on the encoder side. So you can see that they share the identical structure, they share the identical input signal, and this input signal is nothing else but the quantized prediction residual. So this is the prediction residual, this is the quantized prediction residual. It is sent to the decoder as some kind of index for each of the time samples A of n. So I have the quantized version of A of n. Okay? So after the break, we will show the demonstration of such system and how they operate on an example of speech waveforms. So if we apply this linear prediction technique, both open loop and closed loop, I will apply it to speech signal. We will apply it to vowels. So vowels are these long duration sounds in speech, and in Croatian language you have these 5 primary vowels: a, e, I, o, u, o. A, e, I, o, u. Sorry, a, e, I, o, u. And the final, the 6th vowel is this neutral vowel. So it is not used in constructing normal words, but it is used when you want to say something but you cannot remember. For example, now it's 8 o'clock. Okay, I don't know what to say. So this is some kind of filler sound. For example, in the English language, they have 11 different vowels, much higher number of vowels than in Slavic languages. The Slavic languages are rather, I would say, poor with vowels, with only 5 primary vowels. And that is one of the reasons that people with Slavic origin can really never learn to pronounce English words correctly, because they simply convert one of those 11 vowels in English language to the closest one of only 5 discrete vowels in Croatian or Slavic source, let's say. So they will immediately recognize someone is a Slavic speaker because he completely distorts the original vowel to one of those 5 that are available in Slavic languages. Okay, so we will show how this sound A, E, I, O, U, can be efficiently quantized using linear prediction. Okay, now we have break. Continue. So now we will introduce how this concept of linear prediction was first applied for coding of speech. And that is something that you constantly use each day, each second that you use your telephone. So each of you, when you're communicating with your friends over mobile phone, either it is over 4G network or it is over WhatsApp or whatever kind of program you are using, you are actually applying speech coding based on linear prediction. And how is it done? As I said, speech signal is almost very close, theoretically very, very close to the linear prediction model. Because when I try to model the acoustic properties of vocal tract, so if I want to really model how the speech signal is generated in vocal tract, then we will get the final solution or final equations which naturally lead to the linear predictive coding as such. So the model that is used to describe the way that acoustic waveform is formed in your vocal tract, the final solution is actually the form of a linear predictor. And as I said, what we are trying to utilize in linear prediction are correlations. That certain part of signal is correlated with something that follows. Okay, so preceding part of the signal is correlated to the sample that is being predicted, and we divide this correlation for speech in two types of correlation. One type of correlation are the short-term correlation, and they are related to the vocal tract activity. And the other type of correlation are the so-called long-term correlation, and they are related to the process of excitation of the vocal tract. And for the vocal tract, we recognize two basic modes or two basic types of excitation. And these are either voiced excitation, and this is the case when you have a voiced sound. So all the vowels are voiced, some consonants are voiced, but some are unvoiced. But to check whether it is voiced or not, you simply put your finger here on this Adam's apple or whatever, and you can feel the vibration. But if you are pronouncing s, nothing moves. So there are no vibrations when pronouncing unvoiced sounds. So only for voiced sounds, I have vibration of vocal cords. And this vibration is some kind of periodic or pseudo-periodic excitation. I have a period that is repeating itself quite nicely from one period to another period. Practically, I have the same excitation that is just repeated. And this would be the long-term correlations. Short-term correlations are related to the shape of vocal tract. And shape of vocal tract are primarily determined by your tongue. As your tongue moves in this mouth cavity, it creates a volume. The shape of this volume is varying with time. And the shape of this free air volume is the one that defines the sound that is produced. The excitation is always the same. The only thing that changes is this shape of the vocal tract. And for different shapes, I would have different sounds. It is very much similar to this horn or whatever kind of instrument that you use. When they want to produce different pitch, they will try to change the geometry of this tube. By changing the geometry of the tube, they will have a different sound coming from the horn or whatever. Okay. Linear predictive coding was successfully applied to both, to model and utilize short-term correlation that are related to the shape of vocal tract and its changes with time, as well as long-term correlations which are related to vibration of vocal cords, vocal folds. Okay, it is shown here. So this here is one segment of speech signal of duration, I would say maybe 10 milliseconds or 20 milliseconds, something like that. And here you see one period of glottal opening and closing. So these vocal folds are opening, closing, opening, closing. The frequency of this natural or fundamental frequency is of the order of 60 hertz for male speakers, maybe 90 hertz for female speakers, or a bit more, maybe 100 something hertz. And it can be very high, almost 300 hertz for little children. So they have really high-pitched voice sounds, okay? And for male speakers, this period will be then reciprocal of this 60 hertz. So around 16 milliseconds is the duration of one opening and closing of these vocal folds. And this here is one such period, okay? And this period is obviously very similar to the next period, So each time your vocal folds open and close, they'll produce more or less similar waveform for each period. But this would then be related to these long-term correlations. The two successive periods, two successive glottal pulses are similar, and we can use this similarity to predict this sample from this sample, this sample from this sample. Okay, so we have the similarity on between some distant samples. This here is index 1060, and this here is 1140, for example. So we have 100 samples displacement between these two samples. And of course, this changes with time, because when I have the natural pronunciation, my pitch is varying. I don't have constant frequency. If I would have a constant frequency, then you will say this is monotonic speech. I am speaking with the same frequency. I am speaking today, blah, blah. Okay, when I keep the pitch frequency constant, then it is like a monotonic speech. But as soon as you want to convey some, let's say, whatever, meta information, then you introduce this prosody, this variation of pitch, and this variation of pitch is crucial for natural speech. Okay, because you not only hear what I'm saying, but I also understand it is the beginning of the sentence, whether it is an interrogative sentence or it is a definite answer to something. Okay, so it is all related to pitch. So this period is changing with time, and we constantly have to adjust this prediction difference in time to follow this time varying pitch. The other correlation is related to the neighboring samples. So if I magnify this region here, so if I magnify this region, I would see something like this. And these red samples are those that I used to predict this green sample here. That was exactly as was illustrated before in this example in this plot. Where? In this plot. Okay, I use 10 preceding samples to predict green sample. And this kind of correlation is short-term correlation, and these are related to the shape of the vocal tract and its changes. So how the shape of the vocal tract changes during pronunciation of each sound. Okay, going back. Okay, now we have said that just to show you how successive glottal pulses are similar, if I extract neighboring periods, this period, this period, this period, and align them at the beginning, I would get some kind of overlap plot, and you see that the period is definitely changing with time, because they are not exactly overlapping, but they are like stretched a bit. One is more maybe longer, the other is shorter, but nevertheless they behave similarly for all of the neighboring glottal pulses. Okay, that we have explained. These vocal tract characteristics that are modeled by short-term correlations are directly related to the so-called formants. Formants are frequencies where your vocal tract has a significant gain. So, for example, the excitation signal coming from your vocal cords is amplified when the frequency of this excitation is around 800 Hertz, 1200, then 2500 Hertz, 3.7 or 4 point whatever. So these positions, this frequency where the input spectrum of the excitation is amplified are called formants, speech formants. And these speech formants are characteristic for each vowel. So, for example, this is for vowel R. The positions of this maxima is characteristic for the sound R. But if I pronounce A, then they will shift. They will have another set of frequencies where the formats occur. Okay? And the way to analyze speech is through, also one possibility is to apply spectrograms. Because this here is one spectra or one spectrum of one short speech segment. For example, I have extracted this kind of speech segment, and I have computed spectrum of this short, let's say 20 milliseconds or 30 milliseconds of speech. And I would get a spectrum that looks like this, but it is not actually a spectrum. It is only a spectral envelope. It is like an energy envelope of the spectrum, because the actual spectrum also contains the excitation. So if these are the formants, for example, the actual spectrum has this shape. Because this red are individual harmonics of your vocal folds, of your excitation signal. The excitation signal is periodic, and that means that the separation between individual harmonics is always the same. It is F0 or fundamental frequency at which your vocal folds are vibrating. And so if I compute this difference for any pair of harmonics, it will always be F0, F0. It will always be F0. So I have this harmonic structure. I have integer multiples of F0 in the spectrum, and their peak amplitude is defined by this blue curve. And this blue curve is the formant structure. And this blue curve is nothing else but the frequency response of the LPC model. So the linear predictive model, this filter H of Z, that we have found out through linear prediction estimation, this reciprocal H of Z, its frequency response is exactly this envelope that defines how each of the pitch harmonics is amplified by your vocal tract. And that depends on the sound that you are uttering, that you are producing. So if it's sound R, then it is this set of frequencies that are amplified. If it is A, another set of frequencies, okay? And if I repeat this spectrum analysis in time, for first block, another block, I would get a spectrogram. to be able to show how the spectrum changes with time. And this spectral evolution is then shown in such two-dimensional plot. Now this is time domain, this is frequency domain, and one spectrum of this kind is like a vertical slice of this two-dimensional representation, vertical slice, but now the amplitude is shown with the color. So since I cannot show the third axis, z-axis, I have only x and y, x is time and y is frequency. I will show the amplitude in color. Higher the amplitude, then it is rather a bit lower is yellow, a bit lower is green, and very low amplitude is blue. And this amplitude is shown also in logarithmic scale, not in linear scale, because this logarithmic scale is compliant with our way that we perceive sounds. Okay, and now this red pulses caused by individual harmonics of your excitation are actually these lines. So if I take this vertical cut, I will have this first line, second line, third line, blah, blah. So these are these individual lines. And some lines are higher. For example, these lines are higher, these lines are higher. So obviously, I have first format here, second format here, third format here, and the fourth format is somewhere at the edge of the spectrum, on the highest edge, close to half of the sampling rate. So the highest frequency is half of the sampling rate. This kind of spectrogram is called narrowband spectrogram, in contrast to wideband spectrogram. Wideband spectrogram of the same speech signal or short sentence, it is one word, sa. So this recording was two phonemes, s and then a. S, a. So you can first of all see that s doesn't have this harmonic structure. Why? Because we don't have periodic excitation of vocal folds for unvoiced sound s. So it has some kind of noise-like spectrum without any periodicity, without these pulses, red pulses. On the other hand, this vowel a has very nice periodic structure, so we can really recognize individual harmonics of the excitation signal. And these harmonics are displaced exactly F0, fundamental frequency. That is the frequency at which your vocal folds are vibrating. But you can see here for the last harmonic that this frequency is not exactly constant, but also changes with time. Because this is simply, for example, this is 2F0, 3F0, 4F0. This 1F0 is not shown because it is cut by the pre-filter. Pre-filter removes this very low part of the spectrum. So this here is a DC component on the bottom, and a certain part, maybe from 300 Hertz, is only then passed through the pre-processing stage of speech. And that is the reason you don't have this first harmonic. So this is first harmonic, second, third, fourth, fifth, fifth, sixth, 7, 8, 9, 10. So this may be 25th harmonic. So this 25th or 24th harmonic is nothing else but the 24 times fundamental frequency. So as the fundamental frequency changes, so I will see it much better with higher harmonics, because simply it is emphasized 24 times, the variation of the fundamental frequency. So it also happens here, but I don't see it because the frequency is small. Okay. Now, if I do the wideband spectrogram, I get this kind of image, and this image actually shows much nicer the position of formants. So this red region is the first formant, something related to the, let's say, peak at 800 Hertz of your transfer function of the vocal tract. So the vocal tract amplifies frequencies around 800 Hertz. And that is shown here with this red color that we have high amplitude in this region around 800 Hertz. The same is around 1.2 kilohertz. Then the third formant is at 2.5 kilohertz and the last formant at 3.8. So now I can easily see the formant structure of the speech by using wideband spectrogram. And the only difference between wideband spectrogram and narrowband spectrogram is the width of the time segment that is used for analysis. If the speech time segment is rather wide, around 25 or 30 milliseconds, in a way that it encloses at least 2 or 3 glottal pulses, very much similar to the segment shown here. I have 1, 2, 3, almost 4 periods of periodic speech enclosed within this analysis window. For such wide analysis window, I will get this narrowband spectrogram. Narrowband spectrogram where I have individual harmonics clearly shown. But if I take a rather narrow analysis window, and that would mean that the analysis window is comparable to the width of the glottal pulse, or even shorter. So if I take this kind of analysis window, and if I move it in time, I would get wideband spectrogram. So this wideband spectrogram is when you do the spectrum analysis on very narrow time windows. Okay, and just as a curiosity, let's say that people, experts, were trained to really read what you have said or what you have pronounced by observing this kind of spectrogram. At that time, it was only grayscale, they didn't have color, so it was printed on some kind of tape with black meaning high amplitude and white meaning no amplitude. And these experts were trained to really recognize immediately from the image which sound you produce, so which was, for example, sentence based on this graphical representation of the spectrogram. And just to be a very interesting fact is that nowadays one of the most sophisticated architecture for speech recognition is based exactly on this concept. You first convert speech signal to image of this kind, to either narrowband or wideband spectrogram. And then you apply techniques that are used for image analysis and image recognition. So nowadays, these deep neural networks based on convolutional layers and these fully connected layers are very successful in recognizing images. So, for example, try to find all the images containing the German Shepherd, and immediately you get the list of images that have whatever German Shepherd in them. But the same technique can be used here just to, let's say, find characteristic images of certain sounds. So nowadays, one of those systems that have the highest score or the least word error rate are based on this conversion of speech to images and applying image recognition algorithms based on deep neural networks to decode speech, to convert speech into text. So automatic speech recognition. Okay, going further. The concept of or the physics of speech was already studied quite long ago. So, for example, in 1791, one scientist, Wolfgang von Kempelen, he designed a mechanical device that could speak under the control of the operator. So he produced like a synthesizer, but based on mechanical, let's say, human intervention. And the drawings of his idea are not shown here. So you have this source of, how it is called, I don't know, the same, that thing that used by blacksmiths to create fire, to heat the iron. So it is like, it blows air through this tube by pressing this harmonica thing. And then there's also part that creates vibrations, and this is very much similar to these wind instruments like flute or whatever. You have this reed, and this reed vibrates in the airflow stream. And it was also present in this contraption of his that for voice that should be, for sounds that should be voiced, then this excitation was periodic in the same way as you have it in the flute. Okay? And then also he constructed like something that resembles vocal tract, and that was controlled by fingers, by hand. So you would move some levers, and based on this movement, this volume would change its shape. And then you would simulate something similar to what happens in the actual vocal tract when you move your tongue, when you move your jaw, and so on. And the actual device that he designed is exhibited in Deutsches Museum von Meisterwerken Naturwissenschaftstechnik in München. Okay, so that was the first mechanical synthesizer of speech. And in 1939, it was the first time that electronic synthesis or electric synthesis of speech was achieved. And it was done during the World Fair that was held in 1939 in New York. So just before the Second World War, there was this World Fair in New York. And as some kind of greatest miracle of that time, this Voder, voice-operated recorder, was demonstrated. And it was designed, it was proposed by this guy, Homer Dudley. How it looked like, this is a huge hall in this fair room, whatever, fair hall. And it says here the Voder, and you see how this Voder was controlled using some kind of keys. So it has 10 keys, 5 for the left hand, 5 keys for the right hand. Also it had some kind of pedal, pitch control pedal, and a pitch control knob to change, I don't know what. But there was a wrist bar that you can change from vowels to consonants or reverse. So on the left hand, if you move your wrist up or down, you change this type of excitation, whether it is voiced or unvoiced excitation. So this lady shown here in the middle, so she is sitting in front of this user input device, and she is, let's say, like playing this keyboard and controlling the whole system, and then this system reproduces this synthesized speech on some speaker. And hopefully, let me try. I will try to run example of this synthesized speech. Why doesn't? It is turned off. Okay, escape. Is it here? No, I think it is. It was reformatted, so I have to go to web. Let's try this. Firefox. Okay, fair. Okay. Intranet, multimedia system, English, lectures. And now we will save this MATLAB demonstration for lectures. Audio examples used on the third lecture. Okay. Show all downloads. Okay, I'll try to play it. Finish, whatever. Finish.
Will you please make the voter say for our Eastern listeners, good evening, radio audience. And now for our Western listeners, say, good afternoon, radio audience.
Good afternoon, radio audience.
So the first part is the real human speaker, and then you have the synthesized speech. Again, the real speaker and another synthesized speech. So I'll play it again. So it is...
Will you please make the voters say for our Eastern listeners, good evening, radio audience.
Good evening, radio audience.
And now for our Western listeners, say, good afternoon, radio audience.
Good afternoon, radio audience.
Okay, so it is not of great quality, but of course it was very complicated to run it. And they, I think, trained several tens of these operators to run this system. It was quite complicated to have a natural speech coming out of it, because obviously they had to type this very fast, these keys, to have this normal dynamics of speech, and change each time for each sound, whether it is sound or voice to unvoice, to change the level with the pedal and so on, and change the pitch frequency as well. And actually it was designed by this big telecom company, AT&T, and the idea was that it would be used for secure communication over the ocean between the allies, let's say between the US and UK. So let's say at that time President of US would communicate with Prime Minister in UK, but they never used it really because Churchill hated it. So he said, this is of poor quality, I don't want to hear this. Just call me with a normal phone and we'll talk. So, or but just send a courier and then we'll get information that is secure. So that was the idea, to avoid eavesdropping on the telephone cables, lines that cross the ocean. They tried to apply this for cryptographic encryption of the speech, such that it cannot be eavesdropped by some enemy. And but nevertheless, due to poor quality, it was not really used. But the system was installed. I don't know, in Whitehall in London, in some basement, there was this system installed, and it operated digitally. So whatever it was keyed in US, it was transmitted digitally over the telephone lines, and it was then synthesized on the other side using this voder. Okay, so this is this voder. Okay, going further to the presentation. But then a real breakthrough came with computers. So when first computers were designed and when they were successfully used in engineering, they decided why not to use computers to do this kind of predictive speech coding based on linear prediction. And it was proposed in Japan version of this AT&T that was called Entity in Japan, and this Itakura Fumitada worked in this Entity, and he proposed in 1966, he proposed the idea to encode speech using linear prediction. And it was described in one paper published in internal journal of this entity Tokyo, Electrical Communication Laboratory, entity Tokyo, report 3107, the theoretical consideration of statistically optimal methods for speech spectral density, written by Saito and Itakura. And at that time, when they described this system, it consists of what? Computing these correlation coefficients that we described just earlier. This R of 0, R of 1, blah, blah, blah. Okay? So I compute these autocorrelation coefficients. Once I have these autocorrelation coefficients, I form a linear system of equations. So this matrix that now, instead of phi, becomes matrix R. And what you have to do, you have to find the inverse of this R and multiply it with this right-hand column that contains autocorrelation coefficients for R of 1 to R of P. Once I have this optimal solution, okay, you simply construct a filter and find this prediction residual. This prediction residual is then classified whether it is voiced or unvoiced. And then based on this binary selection, voiced or unvoiced, the reconstruction is done by passing the synthetic excitation source through the filter. This here is just this filter H of Z. Nothing else but this inverse filter H of Z that does the reconstruction. You can see the original coefficients, alpha 1, and these are these delay elements, Z to the minus 1 times alpha 1, Z to the minus 2 times alpha 2, okay, and they construct prediction, and it is added or subtracted, whatever, and input source is not the quantized prediction residual, but some kind of synthetic excitation, which is either white noise or the other way, periodic train pulse. So 1, 0, 0, 1, 0, 0, 0, 1, 0, 0. So they create just a periodic train pulse on chosen period. It's called pitch period. So for example, these unit pulses are displaced 80 cycles. And they create this kind of ideal periodic excitation that is then filtered with this filter H of Z. And this is nothing else but the basic of so-called LPC vocoder. LPC vocoder is this kind of structure. Okay? So it has this reconstruction filter H of Z, whose coefficients, alpha 1 to alpha p, were found through linear predictive analysis. So we solved this linear system equation on a short speech segment. And we have found optimal coefficients, alpha 1 to alpha, typically p is equal to 10. Typically the order of prediction is 10th order. For the laboratory exercise, we will experiment by varying this order from 4, 6 up to 10 to just see or hear what happens depending on the chosen order. So this time varying filter, it has this set of parameters for one short segment. For another segment, I will compute a new set of parameters and synthesize speech using this kind of optimal set, 10 numbers, alpha 1 to alpha 10. Therefore, next segment, again, 10 new numbers. But these segments are typically 20 or 25 milliseconds long. And the overlap, it doesn't have to be large, maybe 10 milliseconds overlap between neighboring segments, but more or less, you have at most 50 frames per second. So you have to compute new set of coefficients, 50, at most 100 times per second, and then use them for this interval as a constant set of coefficients. Okay, so this is like a stepwise varying filter. I compute one set of coefficients and I use them for 10 milliseconds or maybe 20 milliseconds. Then I compute a new set of coefficients, again, use them 20 milliseconds. Okay. And the excitation is, again, either generator of random noise, completely like a Gaussian random noise. It doesn't have any parameter. It is only amplified with a gain factor, and this gain factor is something that is used to model the varying level of speech, so the varying intensity of speech. So if I want to vary the intensity, I must have this gain factor as a part of the model. And for the voice speech, I have this ideal train pulse. So I have one, and then pp minus 1, zeros, pp minus 1. Again, 1 and pp minus 1, zeros. And this pitch period is also changing with time, mimicking the change of your fundamental frequency, so how your vocal folds are changing with frequency during normal pronunciation. It is also amplified with the gain factor and passed through this filter. Okay? And now I will go to the demonstration. Let's say that I have analyzed speech in this way, and that I have found this set of coefficients for speech segments of 20 milliseconds in length. So this is the original sound.
glass.
So if I now do this LPC vocoder-based modeling, I will have the reconstructed speech that looks like, let me check, this.
glass.
Slightly distorted, slightly of lower level, but nevertheless sounds quite similar.
glass.
Okay, so this is the original, but passed through this LPC vocoder. And what it does, it is shown in these slides. What it does, okay, so it computes gain term. So you see here, I have to find the gain term for each frame, for each analysis frame. What is the factor G, gain term? And on the bottom, you have these phonemes, sounds that I'm pronouncing. Ovo, je, moj, glas. Okay? So you see that the amplitude is rather high, only for vowels. O, oi, o, a. So for vowels, the amplitude is rather strong. Then another parameter of the model is set of coefficients. In this example, I use 10 coefficients, alpha 1 to alpha 10. And these here are these coefficients of the filter A of Z. And of course, the H of Z has the same set of coefficients, but in the denominator. As time goes from frame 0 to frame 140, I see the evolution of each individual coefficient. I don't know, blue probably is alpha 1, then whatever color is alpha 2. So how these coefficients, alpha 1, alpha 2, are changing with time. And the final part of the model is the pitch period. So what is the period of excitation for sounds in the periodic? So only for voiced sounds over here, this part, all of these sounds are voiced. Oi, again, voiced sounds. A, gla, gla, all three sounds are voiced, gla, but s is unvoiced. S is unvoiced sound, so I don't have any period. So for all unvoiced sounds, for all breaks, for all pauses, I have 0 period, while for sounds that are voiced, I have the period that has some natural envelope, natural evolution. this evolution of this speech period is due to the intonation. While pronouncing this sentence, I pronounce it with deliberate intonation. Ovo je moj glas, ovo je moj glas. So larger period means lower frequency, lower fundamental frequency. Okay, so this is the third model parameter. So we have this set of coefficients alpha 1 to alpha 10. We have gain term, and we have either voiced or unvoiced. So if it is voiced, then what is the period? If it is unvoiced, let's say period is 0. So it is position of this switch. For unvoiced sounds, I generate random noise source. For voiced sounds, I create this periodic pulse train excitation. And using these parameters, which are sampled in our case with 100 frames per second, so the idea is I advance by 10 milliseconds for each new frame. Each new analysis frame is 46 milliseconds wide, but I move only for 10 milliseconds steps. And I get, so this is the gain term, these are the coefficients alpha 1 to alpha 10, this is the pitch period, and this is the voiced, unvoiced binary decision. Voiced, unvoiced, voiced, unvoiced, voiced, unvoiced, okay? And if I compute the wideband spectrogram of the original speech, of the input speech, it is this spectrogram. And this is the spectrogram of this synthetic LPC output. And it is the one that I have just played. So this second example, this glass no,
Ovo je moj glas.
it has this wideband spectrogram. On the other hand, the original sound was this glass,
Ovo je moj glas.
and its spectrogram is this one. So you can see that these spectrograms are, let's say, not exactly equal, but similar, and sounds, they also sound similar. So both sentences sound similar, input and output. But what you can do easily with this model, you can do any kind of modifications that you desire. So nowadays it is also very interesting with this deep fake. You create false, let's say, voice. You create a voice of another person and you say a sentence, but it sounds as whatever. Donald Trump has said this sentence. So it can be done also with vocoder in a very simple manner. For example, I want to create false pitch. I will create the voice sound that is of twice lower frequency or twice higher frequency of vocal chords. These are low and high, I see. Yeah.
Ovo je moj glas.
So
Ovo je moj glas.
2 times lower pitch frequency.
Ovo je moj glas.
Directly synthesized by simply what I'm doing. Instead of using PP as a proper pitch period, I'm using PP times 2 and creating synthetic excitation that has twice longer period. And I get the sound, I get a speech that is quite intelligible, the same message as before, but the voice is completely changed.
Ovo je moj glas.
The other way is if I falsify the pitch period by dividing it by 2, so I have twice higher frequency of pitch variations, of pitch frequency.
Ovo je moj glas. Ovo je moj glas.
Very unnaturally sounding speech.
Ovo je moj glas.
As some, I don't know, sick person, whatever, has a problem with throat.
Ovo je moj glas.
Okay. But also what you can do, you can shorten the sentence by a factor of 2 or lengthen it by a factor of 2 to have a longer pronunciation. Longer first.
Ovo je moj glas.
So the same speaker, the same sentence, but I simply repeat each frame twice.
Ovo je moj glas. Away my glass.
Or what students also prefer when playing YouTube on ×2 to save time, then it is twice shorter.
Away my glass. Away my glass.
So the same sentence, but I skip each second frame. I take one frame, use it for reproduction, but then I skip one frame.
Away my glass. Away my glass.
So again, it sounds natural, but of course twice faster, twice shorter. So these are modifications that you can use, that you can do as soon as you have this kind of parametric speech model. You have parameters, and you can play with parameters any way you like. To change the voice characteristics to some other person, what you have to do, you have to map the set of coefficients alpha 1 to alpha 10 to another non-linearly modified set alpha 1 prime to alpha 10 prime that is characteristic for this second guy. So for example, I have what are the set of coefficients for vowel R for me, but if I do it for colic, then I would get like a mapping. What I have to do with my coefficients, alpha 1 to alpha 10, to produce the same vowel R, but pronounced by a different person. So it does this kind of non-linear modification of the vector from one person to another vector of another person, and it does so for all the sounds I produce, he produces. And it creates this kind of non-linear mapping. It can be also trained by some kind of neural network. You have a large number of vector pairs, and you simply find the transformation from one set of vector to another vector. You have this deep fake solution to create another voice that is really naturally sounding. You cannot distinguish whether it was the actual person or this one that was mimicked, simply like faked, not the actual person, but somebody else said this sentence, but it was transformed to sound like it was spoken by Donald Trump. Okay? We'll make a break now. Now it is 10 minutes past 6, so we will start at 25. Okay? So we have shown that with parametric speech model, we can do very interesting modification of speech signal by either changing the pitch or changing the duration of speech by simple manipulation of these parameters. The linear prediction coding of speech was really applied in the actual standard. And one of the first standard where this direct implementation of vocoder model was done is the LPC10, or also known as Federal Standard 1015. It was a standard that was developed by US Department of Defense as a basis for secure communication, for security communication purposes. It uses 10th order linear prediction model, and that is the source of its name. So the abbreviation LPC10 comes from this P equal to 10 for this coder. The data rate at the input is normal speech sampled at 8 kilo sample per second, and each sample is represented as 8-bit value. So we have input rate of 64 kilobits per second. And output data rate is only 2.4 kilobits. So it achieves 27 times compression of the input rate. Bit assignment for individual parameters of the model is shown here because so far I have not demonstrated what is the influence of quantization. So what happens if the original coefficients A are quantized into some kind of quantized version that is then sent to the decoder to reduce the rate. Because only unquantized version of the original parameters was used for these demonstration purposes, but in LPC10 the parameters are quantized. So A1 to A10 are quantized indirectly through some alternative form of representation, which are called K coefficients. They have one-to-one mapping to A coefficients, so it is nothing very fancy. It's simply some kind of nonlinear transformation from alpha 1 to alpha 10 into K1 to K10 as an alternative representation of these coefficients. So these are all related to vocal tract. And you can see that these first four are quantized with 5 bits. So only 32 levels for K1, K2 up to K4. Then K5 to K8 are quantized with 4 bits, K9 with 3 bits, and K10 with only 2 bits. Pitch is quantized with 7 bits, including the voiced-unvoiced switch. So 1 bit binary information for voiced or unvoiced, plus 6 bits for pitch. And gain term is quantized with 5 bits, but on logarithmic scale. So altogether, when we add up, it is 54 bits per frame. And since the frame advance, or this advance of the analysis frame is 180 samples, and that is 22.5 milliseconds. For 22.5 milliseconds, I will use the same set of coefficients, all of them, pitch, gain, and K1 to K10. And when I multiply this 54 for one frame with this ratio, that I send new set of coefficients only for 180 new speech samples, then I end up with a final rate of 2.4 kilobits per second. Okay. You can download the original C code of this LPC 10 encoder. Maybe this link is still alive, but you can also Google it. There is definitely somewhere around original C code of this LPC encoder. Speech quality is quite poor, but even today it is used in the category of encoders with very low output rate, where the primary focus is on intelligibility and not on the quality. So the only requirement is that the other side should be able to understand what you are telling, and not that you should sound nice or in high quality. So that you don't maybe misrecognize what you have said. The newer revisions of this standard work on a twice lower rate, so 1.2 kilobits per second. So they are capable of encoding intelligible speech with only 1,200 bits per second. How this LPC encoder looked like in early days, in 1974, so this was used for secure communication over radio channels. It weighted 120 kilograms, the whole box, and it enabled the two sides having the two boxes, one on one side, another on the next side, so communicating over the phone, and they were able to understand each other, and nobody could eavesdrop because the bit stream was additionally encrypted to secure it. This vocoder model was also used in music production, and one of the first albums where this vocoder was applied was on this Kraftwerk band on the album Ralph and Florian. So this is the actual vocoder that they were using when recording this album. The newer versions, maybe from 80s, 86, you can see here, of these secure telephones are shown in this image, and they were based on newer standard, Federal Standard 2016, that had a more advanced code-excited linear prediction encoder. Okay, and that's for the last slide for this presentation and what we have learned so far. Now I will open the last presentation, since we have only half an hour left. And this last presentation is introduction to your second laboratory exercise. So since you have the materials to prepare for this laboratory exercise, written materials, I would not go into details, but maybe just emphasize few main facts that you should be able to find out on the actual laboratory to understand. Okay, so we'll make examples of predictive speech coding. Okay, so speech encoder with vocoder structure explained so far rejects completely information about this prediction residual. It only models this excitation as periodic train pulse or as white noise. But the actual form of the prediction residual waveform is ignored, is not transmitted. And so this synthetic excitation only roughly mimics the actual or real vocal tract excitation. And it is logical to expect that if I somehow add additional bits to encode this information about the excitation, I could get better quality. Okay, more naturally reconstructed speech than with LPC coder. So the idea is not to use a primitive model that you have either only voice or unvoiced. If it is unvoiced, it is a random noise. If it is voiced, it is a periodic pulse name with a given pitch period pp. No, but I somehow want to encode this excitation better, or even as close as possible to the original. So this can be achieved in two ways. One way would be to do the open loop prediction, open loop, the quantization of prediction error in open loop, as I have explained so far. As well as alternative approach to use this closed loop approach, where you have a local replica of decoder on the encoder side. And therefore, both sides use the same prediction source. Okay? So we have either open loop prediction error, which is then quantized or transmitted to the receiver, to the decoder, or we can have this closed loop approach. Okay. Although these structures are very similar, the actual behavior and properties of these two predictive coding procedures are quite different. So it is interesting to investigate this in more detail. And we will be illustrating this on vowels, since these are long-lasting voices with slowly changing correlation, and the predictor can be used for longer signal segments, for example, 1/2 second. So these are slowly evolving sounds. The consonants and plosives, for example, are much faster evolving sounds. On the other hand, A, E, O, they are lasting a long period, and they are slowly evolving. So for that reason, we can use the same set of prediction coefficients for a longer segment of speech. Okay? Entropy constrained scalar quantizer will be used to do the quantization in both predictive schemes, as well as in parallel for direct quantization. So if I would do the entropy constrained scalar quantization directly on the input signal, and then we will compare what do I get with the same rate over the channel, but either with direct quantization or with predictive quantization. The quantizer step size will be adjusted such that output entropy for each of the coding structure is identical for the objective comparison. So we will adjust the step size to achieve the same output entropy. And quality assessment can be done either by measuring SQNR, so what is the objectively measured signal to quantization noise ratio, or the other way, subjectively, by listening to the signals at individual points of the coding structure to hear what is the effect of quantization on such a structure, predictive structure. And all characteristic signals of the structure will be graphically displayed. So I will now start a program. First, for the case of open loop predictive speech coding, MT04 open loop predictive Gower. Okay, I'll have to start MATLAB. MATLAB. And do I have files already somewhere or not? Okay, NT04. No. Yes. Yes. But not primary. Okay. This. NT04. MATLAB primary. Here. Okay, I have to find this folder in MATLAB. Okay, the program is MT04 open loop prediction for speech Gower. MT04 open loop prediction. So first of all, we have to select the order of the prediction. And let's say we select 6th order predictor. So you have coefficients alpha 1 to alpha 6. We select the output entropy. Let's select some low, or 2.5 bits per symbol. Then we select which of the vowels we want to analyze. A, E, I, O, U, E. So let's analyze U. So this is the original sound. What now? Okay. I don't know what happened. Going further. So this is the envelope, spectral envelope. So one of this model for sound U. So I can see that I have two formats. First format around 400 Hertz, and second format around 2.4 kilohertz. And this here shows the SQNR for high rate approximation, but this here is for I don't know, is it for direct quantization or predictive quantization? One is, I guess, for, okay, I'll explain that figures later, but let's first play with this program. So if I click here, it should be input signal. Okay, so this is the input signal. So this XP, this is this tilde prediction. So X tilde is designated with XP in this example in MATLAB. X predicted. So original and predicted signal. So they sound quite similar. So prediction is very good in the sense that it sounds almost identical to the original signal. And this here is the prediction residual, the difference between the original input and predicted signal. Okay, so this is the signal that I'm now quantizing. This here is the difference between the original signal and quantized prediction residual. It sounds like a white noise. So the quantization error on this prediction residual is like adding white noise to the proper prediction residual. Okay? And if I do the reconstruction, then this is the reconstructed signal. While this was original. Okay? And this here is the prediction on the decoder side that is different than prediction and on the encoder side. There is not a big difference, but there is a difference, especially if the rate is lower. So we'll run the program again with a lower entropy, lower rate, and in that case, the quantized signal should be of lower quality and more different to the original signal than now. Okay? So altogether, the total difference between the original signal and reconstructed signal is this. It sounds like pronouncing still oo, but without vibrating your vocal cords, like a whispered version of vowel, like this. So you avoid vibrating your vocal cords, like whispering, or for a, or for a. So this is this error that sounds like an original vowel, but not with proper voice excitation, but with unvoiced excitation. So that is the reason. So this error is present here, but you cannot hear it. Why? Because it has similar spectrum shape as the original signal. So it is hidden behind the spectrum of the original signal. But if I quantize this signal directly with entropy constrained scalar quantizer with the same output rate, I get this. So there's quite a lot of noise now here. And the error is something that is like white noise, but due to low entropy, you can still hear part of the speech even in the error. So even in the error, you can still maybe recognize some sounds from the original oo. Okay, so this is direct quantization with chosen, I think it was 2.5 bits. And this is predictive. So this sounds definitely much better, much more natural. Okay, but now if I, for example, repeat this, but with even lower 6th order prediction, but now with a rate of only, let's say, 1.5 bit for O, original sound. Okay, input, then prediction, prediction residual. Okay, so this is being quantized with this error. And after reconstruction, I get this. So still, I hear O, but there is in background this error. If I only play the error, so it is like a like unvoiced version of O, together with O. But if I do the direct quantization, then it sounds much worse. So it also plots different waveforms. You have this direct quantized signal with such low entropy. It has only 3 levels: 0, positive amplitude, negative amplitude. Because to have this low output entropy, the quantization step is that large that I have only 3 symbols: minus amplitude, 0, plus amplitude. Okay? And you can see that in the spectrum, I still observe first few harmonics that are within the first format. But practically all other formats, all other harmonics are drowned in the noise. So I actually hear only intelligible part of speech in very low frequency region. On the other hand, if I do the predictive quantization, this is the waveform of this output, this XRQ. XRQ. predictively quantized signal. It looks definitely much better than this A0 minus A. And if I plot the spectrum, now the spectrum is even better resembling the original speech spectra. So I have this first format, second format, also the third format, and I have the periodic structure maybe in this part of the spectrum. It is a bit lost in the upper part, but nevertheless, this spectrum is much more naturally sounding than the direct quantization with the same entropy. Okay, and maybe run it again for another sound, but with higher prediction order. Let's say that we use 10th order predictor, and we select entropy, I don't know, 2 bits. And for E, for example, E. So you can see now with 10th order predictor, we have first, second, third, fourth. We have 4 formats clearly visible, because for 10th order there might be at most 5 formats. So half of the order is the maximum number of formats. But if some formats are at either 0 frequency, or if some poles are at 0 frequency and half sampling rate, then these are real poles, so I don't have this 5th format as is the case now. So I have actually 4 formats modeled by the 10th order prediction, and I have 2 real roots that otherwise would form the 5th format. Okay, so I can either have 2 real roots plus 4 formats, or I can have 5 formats. So it depends on the actual sound, on the results of LPC analysis. So this here is the spectrum, the spectral envelope for sound E. Again, the same image. So, sorry. So this here is the, it has quite a lot of images. You can see figure 9. I cannot open them all because it shows prediction error, quantized version of prediction error, blah, blah, blah. But again, if I click it here, original signal, predicted, prediction residual. So as you click here, it automatically focuses the corresponding figure that shows, for example, in this case, prediction residual, pogreška predikcije, EO. If I click at EO, it automatically opens this figure 3 that plots prediction residual in time domain and in frequency domain. And as you can see, this prediction residual has approximately flat spectrum. So all these harmonics, they have approximately equal amplitude, while the actual spectrum is modeled by the predictor model, because once I pass this quantized prediction to the filter age of Z, this is age of Z, this filter, I get this. So now these harmonics are modulated with the envelope introduced by the model age of Z. So age of Z amplifies certain harmonics. As I have shown, I have first format somewhere low at 400 Hertz, and I have 3 formats somewhere up for second, third, fourth format in the upper part of the spectrum. So this is the reconstructed signal. Again, if I run the difference, so now you see that this difference is practically a random noise, but it has the spectrum very much similar to the spectrum of E. So the spectral envelope of the error follows the spectrum of the original sound E. And if I have such a match, then I can really hide this error behind the larger amplitude signal E. So this error is of the same shape, same spectral shape, but it is of unvoiced character, while the proper signal has the same spectral envelope, but it has voiced characteristics. So if I plot only this X, so you see that it has this similar spectral shape. It doesn't want to be shown in comparison. Okay, so this here is also obvious here as first format. Then this second, third, fourth format, second, third, fourth format. Okay, so the envelope is similar, but I have in the original signal I have this periodic harmonic structure. I can visualize each individual harmonic. For the quantized, for the reconstructed speech signal, it is also very much similar to the original. Okay, if you compare these two. So they look almost identical. But if I click on this directly quantized signal, it is completely different. So you can see that now all of these harmonics are drowned in the noise. So this region that has this nice harmonic structure, but it is of lower amplitude, is now completely covered with noise. Also, the upper parts, okay, so I can still resemble the original spectrum here, but nevertheless, this part is significantly affected. So this is the case for open loop prediction. Now I will end this and run the same example, but for the closed loop case. I have to run the program MT04 ADPCM Goer. Okay, now again I select the prediction order. Let's select some low order for entropy. Let's say I select 2.5 bits, and sound. We have not tried A. Okay, so this is sound A. With only fourth order predictor, I have one format here, only one format here, and I have two roots that are real. One root is here, and one root is here. So actually, with fourth order, in this case, I have constructed the model with only one format. So if I maybe terminate this just to show it with a higher order of prediction, sixth order, the same. Okay, 2 bits. A. Now I have one format here. I actually have 3 formats now. One format is here, another is almost next to it, so practically overlapping, and the third format is here. Okay? Now the block diagram looks differently than with open loop coding, because now I have this local replica of decoder on the encoding side. Okay, so in order to have the same prediction XP on both sides, even for the encoder side, for the sender, I have to do the quantization and use the reconstructed speech as a source for prediction. So this is the original A, and this here is predictively quantized in a closed loop A. So now they really sound similar, and you can also track compare the spectrums of these two. So this is the original, and this is the quantized. So what happens is now that I can see that they are similar, but nevertheless I still observe this noise that is added to the spectrum. And this noise is really white noise that is added to the ideal spectrum. That is really white noise. You can check easily by comparing the original and quantized version. now you can see that the spectrum is practically totally flat. So the error is really complete white noise. In time domain as some kind of random signal, and in spectral domain as white noise. And here I can hear the prediction of the signal. But obviously it is a bit noisy. So with the open loop, prediction was clean because it was computed from the original signal. Now the prediction is computed from the quantized signal. So definitely it is affected by the quantization error. So this XP is affected by this difference that is not zero. This is the original. And this is the prediction error or difference. Okay, so it is the one that is being quantized. So this signal, this EC, is being quantized with this entropy constrained scalar quantizer, and it has the same output rate, same output entropy as direct quantization of the input speech. So we can play the direct quantized version. You can see that it has only small number of discrete levels. 1, 2, 3, 4, 5, 6, 7 levels. Because the rate is very low, and obviously the step size is chosen as a large step, and it cannot do better than that. But if I do the predictive quantization in a closed loop, I get this. This. So you have to compare this figure with this figure. This is direct quantization with obvious discretization of amplitude, but now with predictive quantization, it is much better. So it really resembles the original waveform. This is the original waveform. So the reconstructed speech looks like the original. It has the spectrum similar to the original and much better than the direct quantization. So with direct quantization, this noise level is much higher. This contamination is of much higher amplitude than the white noise added in the predictive loop. Okay? In the closed loop predictive loop. This would be the topic of your second laboratory. And the same thing can be also repeated for images, but you don't have any time. You have only 2 minutes. If I do it for the images, I'll do only for closed loop case. I run the program, Control C, whatever, empty ADPC in, I think it is called Slicker. Okay, now you select the order of prediction, let's say order 2, entropy, also 2 bits, and demo, I don't know, demo 3. So this is the original, I have to close all the figures, clear, close all. Okay, second order predictor, entropy 2 bits, okay, demo 3. So this is the original image. This is the predicted image, and this is the prediction residual. How it looks like, so it is of a larger amplitude only on the edges. So now what this predictor does, it tries to predict central pixel from its neighbors. So if it is a homogeneous region where I have the same intensity for all of the pixels, then practically I have 0 error, because from the neighboring pixels I can ideally reconstruct or predict what is the central pixel. But as soon as I'm on the edge, so this prediction is not good enough. So I have large prediction error on the edges. So obviously what you have in the prediction residual is this kind of edge image of edges. This is the predictor. And to achieve causality, such that I can do the reconstruction, the predictor is not symmetric, that it has 2 pixels up, down, left, right. It has only this causal part that I can start scanning, because I don't have this part yet reconstructed. I have only previous pixels, previous rows, and previous columns to current position. These pixels are already reconstructed on the receiving side, and I can use them to compute the prediction. I cannot use this pixel here to the right, first to the right, second to the right, because this one has to be reconstructed yet. I have not reconstructed this. I have reconstructed only previous rows and previous columns, okay? And now I'm here. So I'm computing prediction of this pixel from this neighborhood, while the value of coefficients, alpha 1 to alpha whatever, is shown with intensity. So higher the intensity, higher the value of this prediction coefficient. Okay, further.